A telescope of metal and gold hangs in the freezing dark, a million miles from Earth. It sits at a special cosmic parking spot where the gravity of Earth and the Sun balance out perfectly. This is the James Webb Space Telescope. We spent 30 years and $10 billion building it. When it finally opened its massive golden mirror, scientists expected it to send back the cosmic equivalent of baby pictures. They thought they would see a young universe filled with messy, chaotic first drafts of galaxies, just loose blobs of gas and infant stars struggling to come together. Instead, the data coming back has left the entire scientific world in absolute shock. Webb looked back to the very beginning of time, and it found the cosmic equivalent of fully built skyscrapers standing where there should have been nothing but dirt tracks. It found giant, perfectly formed galaxies that simply have no business existing yet. It found thick clouds of space dust, made of the exact same chemistry as the smoke from a campfire, drifting in places where it shouldn't have had time to form. It caught signals from the most distant structures ever seen that break our understanding of how stars work. And worst of all, it caught the universe breaking its own speed limit, splitting the rate of cosmic expansion into two completely different numbers that refuse to agree. We are looking at a universe that grew up way too fast. It completely defies the timeline we spent a century figuring out. To understand why this is such a massive headache for scientists, you have to understand one mind-blowing rule of space. A telescope is actually a time machine. Light is fast, but space is unimaginably huge. When you look up at the sun, you aren't seeing it as it looks right now. You are seeing it as it looked 8 minutes ago, because that's how long it took the light to travel to your eyes. When Webb points itself at the darkest corners of space, it catches light that has been traveling for over 13 billion years. Some of the light landing on Webb's mirror today left its home before the Earth existed, before the sun ignited, before the ingredients for life even came together. Every image Webb takes is a photograph of history. For decades, the golden rule of space science was that the universe builds things slowly, brick by brick. After the Big Bang, space was just a hot, featureless fog. Over billions of years, gravity was supposed to slowly pull that fog together into small star clusters, and those clusters were supposed to slowly crash into each other to build big galaxies. But Webb's very first pictures tore up that rulebook. The galaxies it found were too bright, too crowded, and way too big. At first, scientists hoped it was a fluke or a math error, but then Webb locked onto an impossible galaxy named ZFUDS 7329. When researchers looked at the light from this galaxy, they didn't just find a giant, they found an old giant. Its stars weren't young, hot, and blue. They were already old, mature, and dying. By working the clock backward, scientists realized these stars had to form when the universe was only 800 million years old. This galaxy holds as many stars as our modern Milky Way, but it somehow built itself in a tiny fraction of the time. This creates a massive puzzle. To build a galaxy, you need a foundation. In space, that foundation is made of dark matter, an invisible glue that makes up most of the universe. Normally, dark matter slowly clumps together over hundreds of millions of years to create giant invisible bowls. Hydrogen gas falls into these bowls, cools down, and ignites into stars. Because these invisible bowls take a long time to grow, the process cannot be rushed. Gravity doesn't have a fast-forward button. Yet, the foundation for this impossible galaxy somehow grew overnight. Scientists are now desperately scrambling for an explanation. One theory is called the bonfire effect. Normally, when new stars ignite, their intense radiation acts like a thermostat, blowing away nearby gas and slowing down the birth of the next generation of stars. But scientists think that in the ultra-crowded early universe, that thermostat broke. Instead of a controlled burn, these galaxies acted like a massive bonfire. They sucked in all their gas at once, ignited a frenzy of stars all at the same time, and burned white hot before running out of fuel and instantly growing old. If this theory is true, it means every computer simulation we've ever run about the history of space is completely wrong. Another guess is the brightness illusion. Think of a flashlight pointed directly into your eyes. It looks blindingly huge, even if it's actually small. Scientists wonder if these early galaxies are actually normal-sized, but we are catching them during a brief, explosive flash of starbirth that makes them look 10 times bigger than they really are. But Webb is finding far too many of these giant systems for them to all be a lucky guess. The mystery gets even weirder when we look at the chemistry. Webb found heavy space dust that shouldn't exist yet. The first stars were only made of simple hydrogen and helium. Heavy elements like carbon and iron can only be made inside the bellies of stars, and they only spread across space when those stars die and explode. It should have taken generations of stars living and dying to create dust, yet Webb is seeing tons of it drifting out in the open. Right now, the scientific community is split down the middle. Some think we just need to tweak our math. Others are starting to suggest something far more radical, that the laws of gravity and dark matter worked completely differently at the beginning of time than they do today. Every second the James Webb Space Telescope spends out there in the freezing quiet, it keeps sending back data that challenges our neat stories. It is telling us about a universe that didn't wait for permission from our physics textbooks to start building its greatest masterpieces. Webb looked back to an era when the universe was just the beginning, barely a few 100 million years out of the Big Bang, and it found skyscrapers already standing where there should have been nothing but dirt tracks and wooden huts. It detected fully formed, highly structured, gargantuan galaxies that, by all the laws of modern physics, simply have no business existing yet. It picked up chemical fingerprints of complex dust drifting through space where the raw radiation of the cosmos should have shredded it to nothing. It locked onto signals from the most distant structures ever confirmed, carrying anomalies that standard stellar physics cannot explain. And worst of all, it caught the universe breaking its own speed limit, splitting the rate of cosmic expansion into two entirely contradictory numbers that refuse to agree with each other. We are looking at a universe that appears to have grown up too fast, defying the very timeline we spent a century meticulously calculating. To understand why these discoveries have sent a shockwave through astrophysics departments around the world, you have to understand the fundamental trick of how we look at the cosmos. A telescope is not just a magnifying glass, it is a time machine. Light is the fastest thing in existence, traveling at a staggering 186,000 miles every single second. But space is far bigger than fast can keep up with. When you look up at the sun on a clear afternoon, you are seeing it as it existed 8 minutes ago, because that is how long it took for its photons to cross the void to your eyes. When you look at the nearest star system beyond our own, you are looking 4 years into the past. And when Webb points itself at the deepest, blackest patches of empty space, it is catching photons that have been traveling for over 13 billion years. Some of the light landing on Webb's gold-coated mirrors today left its source before the Earth existed, before the sun ignited, before the raw materials for life had even gathered in the dark. Every image is a photograph of history. The established framework of cosmology, the standard model we have refined, peer-reviewed, and run through massive supercomputer simulations for decades, dictates that the universe builds structure slowly, brick by brick. In the wake of the Big Bang, the cosmos was a hot, featureless fog of basic elements. Over hundreds of millions of years, gravity was supposed to slowly pull that gas together, forming tiny clusters of stars that would gradually collide and merge over billions of years to create mature, massive galaxies like our own Milky Way. Our galaxy took a vast expanse of time to reach its current size, slowly devouring smaller systems and methodically converting gas into stars. The universe was supposed to take its time. But Webb's early deep-field images revealed an entirely different reality. The very first batch of data turned up galaxies that were too bright, too numerous, and far too massive for their place in cosmic history. Cosmologists stared at their screens in disbelief. The simulations simply did not allow for objects of that scale to exist so early. At first, there was hope that these early observations were just a temporary glitch, a calibration error, or a handful of statistical anomalies sitting at the extreme edge of a bell curve. But then Webb locked onto an object that dropped like an anchor through the center of the debate, a galaxy cataloged as ZFUDS 7329. When researchers broke down the light coming from this distant system, they didn't just find a massive galaxy, they found an old one. By analyzing the specific chemical signatures and spectra of its stellar populations, an Australian research team determined that the stars within this galaxy were not the short-lived, hot, blue giants you expect to find in a newborn system. They were mature, aging stars that had already been burning for a long time. Working the math backward, the team calculated that these stars had to have formed roughly 3 billion years before the moment Webb photographed them. That pushes the birth of this galaxy back to an era when the universe itself was barely 800 million years old. ZFUDS 7329 contains a mass of stars equivalent to or greater than the modern Milky Way, yet it somehow accomplished the same amount of cosmic growth in a mere fraction of the time, operating in a young universe where raw materials were supposed to be thinly spread and unformed. This creates a severe paradox for our understanding of dark matter. In the standard timeline, normal matter cannot just collapse into a galaxy on its own. It requires a gravitational anchor. That anchor is dark matter, the mysterious, invisible substance that makes up the vast majority of the matter in the universe. According to the blueprints of cosmology, dark matter slowly clumps together under its own gravity after the Big Bang, building massive invisible structures called halos. These halos act like giant gravitational bowls, pulling in hydrogen gas, which then cools, collapses, and ignites into stars. The ultimate size of a galaxy is strictly capped by the size of its dark matter halo. Because these invisible halos grow through the gradual merging of smaller halos, the process cannot be rushed. Gravity does not come with a fast-forward button. Yet for a giant like ZFUDS 7329 to exist when it did, the underlying dark matter foundation would have had to grow to an impossible size ahead of any schedule our models permit. As the data piled up, scientists began desperately searching for an escape hatch to save the standard model. One of the most prominent theories put forward was the idea of bursty star formation. Standard star formation as we see it today is an incredibly inefficient process. In the modern Milky Way, less than 1% of available gas is converted into stars during any given epoch. The rest is kept warm, turbulent, and spread out by the intense radiation and supernova explosions of existing stars, which act like a cosmic thermostat to regulate growth. Some researchers proposed that in the unique, ultra-dense environments of the early universe, this regulatory thermostat completely broke down. Instead of a slow, controlled burn, these early galaxies might have behaved like a massive bonfire, pulling in gas faster than radiation could push it away and triggering a runaway gravitational collapse. They might have converted nearly 100% of their gas into stars all at once, blazing with a white-hot fury before exhausting their fuel supplies and rapidly aging into cosmic seniors. This would explain why they appear so bright and mature to Webb's instruments. However, this theory comes with its own set of uncomfortable complications. If galaxies can achieve that level of absolute star formation efficiency, then every single cosmological simulation ever programmed is fundamentally wrong and needs to be rewritten from scratch. Furthermore, a chaotic, explosive burst of star formation should theoretically leave behind a scrambled, disorganized mess of stars. Yet, many of the ancient galaxies Webb is finding look remarkably tidy, displaying clean disk profiles and organized structures that suggest a settled, rotating system rather than a catastrophic explosion. Another proposed escape route was the brightness illusion theory. This argument suggests that the early galaxies are not actually massive at all, but are merely catching our eyes during a brief moment of intense, temporary brightness. When astronomers calculate the mass of a galaxy billions of light-years away, they have to measure its light output and work backward using an established relationship between brightness and mass. If a relatively small galaxy undergoes a sudden dramatic spike in starbirth, it could temporarily glow with the intensity of an object 10 times its actual size, tricking Webb's detectors into logging it as a heavyweight. But while supercomputer simulations show that these bright flashes can happen, Webb is finding far too many of these giant systems for them all to be temporary illusions. The statistics don't line up. We are seeing a consistent pattern, not a series of lucky glances. The mysteries deepen when we look at the chemistry of the early universe. Webb has detected heavy elements and dust grains in deep space that shouldn't be there yet. The very first generations of stars were supposed to be made entirely of pristine hydrogen and helium, the basic ingredients left behind by the Big Bang. Heavy elements like carbon, oxygen, and iron can only be forged in the nuclear furnaces of stars and distributed across space when those stars die and explode. It should have taken multiple generations of stellar life and death to pollute the cosmos with complex chemistry. Yet, Webb is finding dense clouds of cosmic dust made of the same basic carbon chemistry as the soot from a campfire, drifting more than 100,000 light-years away from any star capable of producing it. The timeline is crowded, compressed, and refusing to cooperate with our textbooks. The tension has broken out into the open, dividing the astronomical community into competing camps. Some scientists argue that we are simply seeing the limits of our current interpretive models, and that subtle adjustments to how dust absorbs light or how stars evolve will eventually bring the observations back into line. Others are beginning to suggest something far more radical, that the fundamental nature of dark matter or the rate at which gravity operated in the infancy of the cosmos was vastly different than it is today. Every second the James Webb Space Telescope spends out there in the freezing quiet, it continues to gather data that challenges our neat narratives. It is whispering a story of a universe that was vibrant, complex, and highly structured right out of the cradle. A cosmos that didn't wait for permission from our physics models to start building its masterworks. We are standing at the edge of a new era of discovery, watching the foundations of cosmology crack, waiting to see what kind of universe we will have to build to replace the one we thought we knew. The debate isn't just happening in quiet university offices anymore. It has spilled over into major astronomy conferences, turning what used to be predictable slideshow presentations into intense, room-dividing arguments. We are watching a live-action rewrite of cosmic history, and every single time the James Webb Space Telescope beams a new package of data back to Earth, the hole we have dug ourselves gets a little bit deeper. To really grip how wild this situation is, we have to look closely at the object that started the modern panic. That impossible galaxy known as ZFUDS 7329. When the Australian research team first pulled its data from the cloud, they assumed they had made a simple formatting mistake or a calibration error. It happens all the time in astronomy. You write a line of code wrong, a decimal point slips, and suddenly a normal cluster of stars looks like an unexplainable monster. So, they hid themselves away for months, running the math over and over from scratch. They checked the telescope's mirror angles. They checked the infrared sensors. They ran alternative calculations to see if maybe a closer galaxy was bending the light and making a small object look massive. Every single safety check came up negative. The data was bulletproof. The galaxy was exactly where it claimed to be, exactly as massive as it appeared, and exactly as old as the physics textbooks said was impossible. Think about the sheer scale of the problem. Our own galaxy, the Milky Way, is a beautiful, mature, slow-cooked masterpiece. It contains billions of stars, massive spiral arms, and complex chemical structures. But it didn't get this way overnight. It took nearly 13 billion years of patient work to become the sprawling cosmic metropolis we live in today. It grew like a real city, starting as tiny neighborhoods of gas that slowly collided, traded materials, and merged over vast stretches of time. It took eras for the Milky Way to gather enough heavy elements, enough stable gravity, and enough internal structure to look organized. Yet, when Webb looks at ZFUDS 7329, it is looking at a galaxy that has the exact same mass and structure as our modern Milky Way, but it managed to build all of that in a tiny fraction of the time. Imagine walking out into a desert where a construction crew just poured the concrete foundation for a house yesterday, and when you look up, there is already a 70-story, fully functioning steel skyscraper standing on the lot. Your brain wouldn't accept it. You would know, logically, that you cannot mix concrete, cure steel, run plumbing, and assemble a skyscraper in 24 hours. The physics of construction sets a strict speed limit on how fast a building can grow. In cosmology, dark matter is the construction crew. It is the invisible scaffolding of the universe. We can't see dark matter, we can't touch it. And despite decades of trying, no laboratory on Earth has ever managed to catch a single particle of it passing through a detector. But we know it's there because we can see its heavy gravity pulling on everything else. Without dark matter acting as a cosmic glue, spinning galaxies would fly apart like mud flung off a bicycle wheel. The standard story of the universe says that immediately after the Big Bang, dark matter started to clump together under its own weight. Because dark matter doesn't interact with light or heat, it was able to collapse much faster than normal gas. It formed these massive, invisible, sphere-shaped structures called dark matter halos. These halos are the literal gravitational foundations of the universe. They act like massive bowls in the fabric of space. Normal hydrogen and helium gas drifting through the void senses the heavy pull of these invisible bowls and falls into them. Once the gas is trapped inside the bowl, it gets squeezed, cools down, collapses under its own pressure, and ignites the very first stars. The catch, and the reason cosmologists are currently losing their minds, is that these invisible dark matter bowls grow through a very slow, very specific process. They start small, and they can only grow bigger by bumping into other small bowls and merging together over hundreds of millions of years. Gravity is a powerful force, but it does not have a fast-forward button. You cannot rush the time it takes for two objects, separated by millions of light years, to drift together and melt into one. The mathematics of our standard model sets a strict floor on how long it takes to build a dark matter bowl big enough to hold a galaxy the size of the Milky Way. And yet, ZFUDS 7329 is sitting inside a dark matter bowl that by all accounts should not have had time to form. The universe was simply too young to have built a foundation that large. It's a paradox that breaks the chain of cause and effect. If the foundation shouldn't exist yet, then the galaxy sitting inside it shouldn't exist yet either. When you run into a wall that big in science, you have two choices. You can declare that your understanding of the universe is broken, or you can start looking for clever loopholes. Naturally, scientists immediately went searching for loopholes, and the most popular one they came up with is a concept called bursty star formation. To understand the bursty theory, you have to realize that star formation in the modern universe is actually a very lazy, inefficient process. Right now, inside the Milky Way, there are massive clouds of cold gas floating around that contain enough raw material to build millions of new stars. But they aren't doing it. Less than 1% of that gas actually collapses into a star during any given era. The reason for this laziness is that stars are incredibly disruptive neighbors. When a giant new star ignites, it doesn't just sit there quietly. It blazes with ferocious radiation and sends out massive stellar winds that act like a giant cosmic leaf blower. This energy slams into the surrounding clouds of gas, heating them up and blowing them away. Because stars can only form out of gas that is extremely cold and perfectly still, this intense heat and turbulence puts the brakes on any further star birth. In essence, a galaxy has a built-in thermostat. The moment it starts making too many stars too quickly, the heat from those newborn stars turns up, pushes the remaining gas away, and shuts the factory down until things cool off again. This self-regulating system ensures that a galaxy grows at a stable, leisurely pace over billions of years. It's a slow, controlled burn. But scientists studying Webb's new data began to wonder, what if that thermostat didn't work in the early universe? What if, in the ultra-dense, hyper-crowded conditions right after the Big Bang, the brakes completely failed? This is the bonfire hypothesis. Imagine taking a massive pile of firewood. If you feed it slowly, one log at a time, you can keep a comfortable, modest campfire burning steadily for a week. But if you douse the entire pile in gasoline and throw a match on it, the whole thing will ignite in a single, terrifying, white-hot explosion. It will release the exact same amount of total energy as the week-long fire, but it will do it all in a single hour, glowing with blinding brightness before collapsing into a pile of cold ash. Scientists think some of these early galaxies might have been cosmic bonfires. Because the gas in the early universe was packed so tightly together, gravity might have been strong enough to completely overwhelm the heat and radiation of new stars. The gas didn't blow away, it just kept falling inward, triggering a runaway collapse. Every single scrap of available gas in the entire galaxy would have ignited almost simultaneously, turning the whole structure into a roaring, blindingly bright furnace. If a galaxy did this, it would form nearly 100% of its stars in a tiny flash of cosmic time, a mere blink of an eye on the scale of the universe. By the time Webb catches the light from this galaxy billions of years later, the bonfire has already ended. The gas is entirely gone, used up in the initial explosion. The stars have already burned through their brightest, youngest phases and aged into cooler, dimmer, mature states. The galaxy looks chemically and structurally ancient because it lived its entire life expectancy in a frantic rush, going from a cosmic newborn to a cosmic senior citizen before the universe was even out of its infancy. At first glance, this theory feels like a lifesaver for the Standard Model. It explains how a galaxy could look so old and so mature without actually violating the age of the universe. If the models just incorporate these sudden, violent bursts of star birth, then the math slides back into place, the impossible galaxies become possible, and everyone can go home happy. But the closer you look at the bonfire explanation, the more uncomfortable it makes people. For one thing, if galaxies in the early universe are capable of turning off their safety thermostats and burning through their fuel with absolute efficiency, then every single computer model, every simulation, and every textbook we have created over the last 50 years about how structure forms in space is fundamentally wrong. We would have to throw out our assumptions about how gas behaves, how radiation interacts with matter, and how feedback systems regulate the growth of space. Even worse, the physics of an explosion don't match what Webb is actually seeing. If you blow up a pile of fireworks, you don't expect the falling sparks to arrange themselves into a neat, organized, rotating grid. A galaxy that forms all of its stars in a sudden, catastrophic, chaotic burst should look like a scrambled, messy blob of stellar shrapnel. It should be an unorganized pile of cosmic ash. Yet, several of the massive early galaxies Webb has locked onto look remarkably neat and tidy. They aren't chaotic blobs, they have elegant disk profiles, clear signs of rotation, and structured shapes that suggest they have settled into a calm, orderly gravitational rhythm. They look like they took their time to get organized, even though they didn't have any time to give. The bonfire theory can explain the brightness, and it might explain the age of the stars, but it cannot explain how a chaotic explosion leaves behind a perfectly ordered masterpiece. This glaring flaw led another group of scientists to champion a different escape hatch, the brightness illusion theory. This idea relies on a simple trick of perception that we experience in everyday life. If you are standing on a dark highway at night, and someone points a high-powered flashlight directly into your eyes, it will look blindingly, overwhelmingly huge. The light saturates your vision, making it impossible to see the actual size of the plastic flashlight or the person holding it. But if that same person turns the flashlight sideways, the illusion vanishes. You see it for what it is, a small, modest light source, not a giant blinding orb. Astronomers calculate the weight of a distant galaxy by measuring the total amount of light it sends across the void, and then applying a known mathematical formula that connects brightness to mass. More stars mean more light, which means a heavier galaxy. But if a relatively small, lightweight galaxy undergoes a sudden, temporary spike in star birth, it will briefly glow with the blinding intensity of an object 10 times its actual weight. If Webb happens to point its mirror at that exact galaxy during its brief moment of intense illumination, the telescope will log it as an impossibly massive giant. In reality, it's just a cosmic lightweight pulling a trick of the light, a small flashlight pointed directly into our eyes. Supercomputer simulations run at various top-tier universities show that these brief flashes of overperformance are mathematically possible. If we are just catching these galaxies at their absolute luckiest, brightest moments, then the standard model survives completely intact. The galaxies aren't actually too big, they are just loud. But this loophole also starts to fall apart when you look at the sheer amount of data Webb is generating. It would be one thing if Webb had found one or two of these blindingly bright objects. You could easily chalk that up to a statistical fluke, a lucky glance at a galaxy having a bright day. But Webb isn't finding one or two, it is turning them up by the dozen. Every deep field image it takes seems to be crowded with these overperforming giants. Statistically, you cannot have every single flashlight on the highway pointed directly at your eyes at the exact same time. The numbers don't work. If Webb is seeing this many bright, structured systems, it means we aren't looking at a temporary illusion or a lucky coincidence. We are looking at a permanent, widespread feature of the early universe. The pattern is real, the weight is real, and the timeline is officially broken. If the size and organization of these galaxies weren't enough to make cosmologists question their career choices, the chemistry Webb is finding has turned the problem into an absolute crisis. When the universe began with the Big Bang, it was chemically barren. The entire cosmos was filled with only 3 basic ingredients: a massive amount of hydrogen, a smaller amount of helium, and a tiny trace of lithium. That was it. There was no carbon, no oxygen, no nitrogen, no iron, and no silicon. This means the very first generation of stars to ignite in the dark, known to scientists as population 3 stars, had to be made entirely of pristine hydrogen and helium gas. Because of the pure chemistry of that early gas, these first stars were theoretical monsters. They were hundreds of times more massive than our Sun, burning with an intense, furious light, and living for only a few million years before dying in spectacular supernova explosions. It is only inside the crushing, multi-million-degree nuclear furnaces of these giant stars that simpler elements like hydrogen are smashed together to forge heavier, more complex elements like carbon and oxygen. And it is only when these stars die and explode that these newly minted heavy elements are blasted out into the void of space, polluting the surrounding gas. This means the chemistry of the universe is on a strict delay. You cannot build complex molecules until you have had multiple generations of stars live, forge heavy elements, die, explode, and seed the universe with the raw materials needed for the next generation. It is a slow, generational pollution of space. Cosmic dust, the kind of microscopic material that gathers in space and eventually clumps together to build rocky planets like Earth, is made of these heavy elements. Specifically, it is often made of complex carbon chains, the exact same basic chemistry as the black soot and smoke that wafts off a campfire when you burn wood. According to every model of cosmic history, it should have taken billions of years of stellar life and death to pollute space with enough carbon to create noticeable clouds of cosmic dust. Yet when Webb pointed its infrared eyes at some of the most distant, ancient regions of space, It didn't find pristine, pure hydrogen gas. It found thick, heavy, drifting clouds of campfire dust. It detected the distinct chemical fingerprints of complex carbon molecules drifting more than 100,000 light-years away from the nearest star capable of making them. Think about how haunting that is. Webb is looking at a region of space so close to the beginning of time that the very first stars should barely be warming up. Instead, it finds space already polluted with the ash of 1,000,000 dead suns. The universe didn't just build its structures too fast. It ran through its entire chemical evolution on a hyper-accelerated schedule. The raw radiation filling the early universe should have been powerful enough to rip these fragile carbon molecules to shreds, yet they are drifting out there in the dark, intact and abundant, completely mocking our neat, clean timelines. The crisis deepens when we look at the ultimate cosmic speed limit, the rate at which the universe is expanding. For nearly a century, astronomers have known that the universe is not static. It is stretching outward in all directions. Galaxies aren't just sitting in space. They are being carried away from each other as the literal fabric of space expands beneath them. The number that describes how fast this expansion is happening is called the Hubble constant, and it is arguably the most important number in all of cosmology. If you know exactly how fast the universe is growing, you can work the clock backward and calculate down to the day exactly how old the universe is. For a long time, scientists had a problem. They couldn't get their measurements of this expansion rate to match up. One group of scientists used telescopes like Hubble to look at relatively close, modern objects, like pulsating stars and exploding supernovas, and calculated how fast they were moving away from us. They came back with one number. Another group of scientists looked at the oldest thing we can see, the cosmic microwave background, which is the leftover heat radiation from the Big Bang itself, a faint glow that fills the entire sky. By analyzing the tiny ripples in this ancient light, they ran the math through our standard model of physics and came back with a completely different, significantly slower number for the expansion rate. This disagreement is known as the Hubble tension, and for years it was the biggest elephant in the room for astrophysics. It meant that either our measurements of the modern universe were wrong, or our understanding of the early universe was wrong. For a long time, defenders of the standard model held out hope that this tension was just an optical illusion caused by the limits of our older telescopes. They argued that space dust or blurry lenses were skewing our measurements of distant stars, and that once a telescope as powerful and precise as Webb was operational, it would clear up the blurriness, correct the errors, and bring the two numbers into perfect, beautiful agreement. Webb got into position, targeted the exact same distant stars, and delivered the sharpest, cleanest data in human history. And it didn't fix the problem, it made it worse. Webb confirmed that the measurements taken by older telescopes were completely accurate. The two numbers do not agree, and they refuse to agree. The rate of cosmic expansion is cleanly split into two values that are mathematically incompatible with each other under our current understanding of physics. It's like measuring the height of a building with a tape measure and getting 30 stories, then measuring it with a laser and getting 40 stories and realizing both tools are working perfectly. This is no longer a minor disagreement over decimal points. It is a fundamental crisis. It means there is a massive gaping hole in the standard model of cosmology. Something is happening out there in the dark fabric of space. Some physical force, some property of dark energy, or some behavior of gravity that we have completely failed to include in our equations. The foundations aren't just showing small cracks, they are actively sliding out from under us. The desperation to fix this has driven some of the most respected minds in physics to start proposing ideas that sound like pure science fiction. One of the most radical theories currently being debated involves an entirely new, completely hypothetical kind of star that has never been directly observed: a dark star. Under standard physics, every star you see when you look up at the night sky runs on a process called nuclear fusion. A star is essentially a giant balancing act. It has a massive amount of gravity pulling all of its gas inward, trying to crush the star into a tiny point. But as that gas gets squeezed tighter and tighter in the core, the heat and pressure rise until hydrogen atoms begin smashing into each other, fusing to create helium. This fusion reaction releases a tremendous amount of outward energy and radiation. This outward push perfectly balances the inward pull of gravity, keeping the star stable, bright, and burning for millions or billions of years. It's a beautifully balanced engine. But a dark star would run on a completely different, terrifyingly efficient power source: the absolute destruction of dark matter. Some theories suggest that dark matter particles are their own antiparticles. This means that if two dark matter particles happen to bump into each other in the dark, they don't just bounce off. They instantly annihilate each other, completely destroying their mass and converting it into pure, raw energy. In the ultra-dense conditions of the very early universe, right after the Big Bang, dark matter was packed together tightly. When the first clouds of normal hydrogen gas started to collapse under gravity, they would have pulled a massive amount of this dense dark matter into the core with them. Inside that crowded core, dark matter particles would have started colliding and annihilating at a frantic rate. The energy released by this dark matter destruction would push outward against the collapsing gas, stopping it from getting squeezed tight enough to trigger normal nuclear fusion. The result would be a dark star, a monster powered not by atomic fusion but by the literal erasure of dark matter. And when I say monster, I mean it on a scale that defies imagination. A normal star, like our Sun, is compact and dense. A dark star would be an absolute leviathan. Because the energy from dark matter annihilation is so powerful but spread out, it would bloat the star into a giant, fluffy, low-density cloud of gas that could grow to be millions of times wider than our Sun and up to 1,000,000 times more massive. A single dark star could be so large and so bright that it would glow with the intensity of an entire galaxy. This is where the theory ties back into Webb's impossible discoveries. Some physicists are now looking at Webb's deep field images and asking a wild question: what if those impossible early galaxies aren't actually galaxies at all? What if they are single, gargantuan individual dark stars? Think about how cleanly that would solve the paradox. If Webb is actually looking at a single massive dark star fueled by dark matter destruction, it would explain why the object looks so incredibly bright so early in history. It wouldn't require a slow, complicated dark matter bowl to form a whole city of billions of stars. It would just require a single massive cloud of gas to trap enough dark matter to ignite a single engine. It would explain the brightness. It would explain the lack of traditional structure, and it would save the timeline of the universe without breaking the Standard Model's rules for galaxy building. Of course, the dark star theory is currently sitting right at the wild edge of theoretical physics. We don't have definitive proof that dark matter particles can annihilate each other, and we haven't yet managed to pull apart the light from one of these early objects clearly enough to prove it's a single giant star rather than a collection of billions of normal ones. But the very fact that serious, tenure-track cosmologists are openly discussing the existence of million-mile-wide dark matter engines shows you exactly how desperate the field has become. The old answers are failing, and the new answers have to be radical to survive. Where does this leave us? Right now, cosmology is split into two distinct mindsets. On one side are the traditionalists, who believe that our fundamental story of the universe is correct, and that these anomalies are just growing pains. They argue that as we gather more data, refine our computer codes, and better understand how dust and gas behave in the extreme environments of the early universe, these impossible observations will eventually smooth out and fit back into the textbook timeline. They see this as a calibration problem, not a philosophy problem. On the other side are the revolutionaries, who look at the cracked foundation, the split expansion rates, the campfire dust, and the old giants standing in a young universe, and see a clear sign that the Standard Model has run its course. They argue that we are making the same mistake ancient astronomers made when they insisted the Earth was the center of the solar system. adding more and more complicated math to force a broken model to fit the sky. They believe we are on the verge of a massive paradigm shift, a total rewrite of physics that will change our understanding of gravity, time, and the dark ingredients that shape reality. Every single time the James Webb Space Telescope shifts its orientation in the absolute zero dark of the L2 point, pointing its golden mirror at another patch of nothingness, it is continuing to read the opening chapters of our history. It is picking up signals that have been traveling through the cold void for 13 billion years, carrying messages from an era we thought we understood. And those messages are clear. The universe is stranger, older, faster, and far more beautiful than our neat little textbooks ever bargained for. It did not wait for our permission to grow up, and it is under no obligation to make sense to our current equations. We are standing on the shore of a vast, uncharted ocean of cosmic history, watching our old maps burn, and realizing that the true journey of understanding has only just begun. The intellectual gridlock has triggered an extraordinary kind of creative desperation across the scientific community. When you walk through the physics departments of major universities right now, you don't find the serene, quiet contemplation people usually associate with high-level research. Instead, you find chaotic whiteboards covered in frantic calculations, intense late-night debates over cold coffee, and a palpable sense that the rug is being pulled from under a century of established science. Cosmologists are finding themselves in an uncomfortable position. They are forced to choose between breaking their understanding of how matter behaves, or breaking their understanding of how time itself flows. To see how deep this rabbit hole goes, we have to look past the giant galaxies and look at the tiny, invisible details Webb is pulling out of the dark. Specifically, we need to talk about the object that sent an actual shockwave through a closed-door meeting of astrophysicists, a tiny, red speck of light cataloged as JADES GSZ 14-0. When Webb first spotted this object, it didn't look like much. On a high-resolution screen, it registers as nothing more than a faint, blurry pixel of deep crimson light buried against a backdrop of velvet blackness. But in astronomy, color tells you everything about distance. Because the universe is expanding, light traveling through space gets stretched out over time. By the time the light from an incredibly distant object reaches Webb, its short, tight blue wavelengths have been stretched out into long, wide infrared wavelengths. This process is called redshift. The higher the redshift number, the longer the light has been traveling and the deeper you are looking into the past. JADES GSZ 14-0 clocked in at a confirmed redshift of over 14. To put that into perspective, that means Webb is seeing this object as it existed a mere 290 million years after the Big Bang. In the grand timeline of the cosmos, which is roughly 8 billion years old, 290 million years is a fraction of a second. It is the cosmic equivalent of looking at a human being who is only a few days old. According to every supercomputer simulation ever run, an object at this absurdly early era should be nothing more than a tiny, chaotic, fragile knot of gas. It should contain a few pristine stars and absolutely nothing else. But when the team used Webb's spectrograph to rip the light from this pixel apart and analyze its chemical barcode, they didn't find a fragile infant. They found a giant. The galaxy was shockingly bright, meaning it was already packed with billions of stars. But the real punch to the gut was the presence of oxygen. Webb's instruments detected unmistakable, heavy signatures of oxygen gas floating inside this ultra-primitive galaxy. This single detail blew the conference room doors off. Oxygen does not just happen. It cannot be created by the Big Bang. The only way to get oxygen into the universe is to forge it inside the nuclear core of a massive star, wait for that star to run out of fuel, watch it collapse, and then wait for it to explode in a catastrophic supernova, scattering its inner chemistry across space. That entire cycle takes time. It requires stars to be born, live out their long lives, die, and blast their remains into the void. For Webb to find massive quantities of oxygen inside a galaxy existing just 290 million years after the beginning of everything means that multiple generations of giant stars had already lived and died before this moment. It means the star-building factory of the universe didn't just start early. It must have hit the ground running at absolute maximum capacity, the literal second the lights turned on. The cosmic clock we've been using to time the history of space doesn't have enough minutes in the hour to allow for this. This realization has forced scientists to confront a terrifying possibility. What if our measurement of the age of the universe itself is fundamentally wrong? For decades, we have confidently stated that the universe is 8 billion years old. We calculated this number by looking at the expansion rate of space and working the math backward to the moment everything was compressed into a single point. It's a clean, elegant calculation. But a rogue group of theoretical physicists has started suggesting that if Webb is seeing fully mature, chemically polluted galaxies this early, then the universe might actually be twice as old as we think, perhaps closer to 26 billion years old. To make that math work, you have to introduce wild new concepts to physics. You have to suggest that the fundamental constants of nature, the numbers that govern the strength of gravity, the speed of light, and the force that holds atoms together, are not actually constant at all. You have to suggest that they change over time, shifting slowly as the universe ages. If the constants of physics were different billions of years ago, then light would travel differently, gravity would pull differently, and our calculations for the age of the cosmos would be completely thrown off. It's an incredibly radical idea, and most mainstream scientists reject it outright, because if you admit the constants of physics can change, you throw open the door to absolute chaos. Every equation we use to understand the world, from the way an airplane flies to the way a planet orbits a star, relies on the assumption that the rules of the game do not change while you are playing. If Webb forces us to admit the rules do change, then we have to rewrite science from scratch. While the theorists argue over the age of time, the observers are stuck trying to figure out how these early galaxies managed to gather so much material so quickly. Even if you ignore the chemistry, the sheer mass of these systems violates a basic rule of nature, the Eddington limit. Named after the legendary astrophysicist Arthur Eddington, this limit describes a fundamental speed safety feature built into the architecture of space. Imagine a massive cosmic object, like a giant star or a growing supermassive black hole, pulling gas toward itself using gravity. As that gas falls inward, it gets squeezed, heats up, and begins to glow with intense radiation. This radiation generates an outward pressure. If the object tries to swallow gas too quickly, it creates so much blinding light and radiation pressure that the outward push completely overpowers the inward pull of gravity. The light literally blows the incoming food away, shutting down the object's growth. The Eddington limit is the universe's way of saying, you can only grow so fast before your own light chokes you. Yet, when we look at the size of the galaxies and the supermassive black holes Webb is discovering in the deep past, they are growing at rates that completely smash through this safety limit. They are swallowing matter with an efficiency that should be physically impossible. They are growing in the shadows, hidden away from their own radiation pressure in ways our modern physics cannot replicate. This has brought the conversation back to the strangest substance in existence, dark matter. Because dark matter doesn't interact with light, it is completely immune to the Eddington limit. Radiation pressure cannot push it away, and light cannot choke it. It can collapse as fast and as violently as it wants, completely ignoring the traffic laws of standard physics. Because of this, an aggressive new school of thought suggests that the early universe was dominated by things called primordial black holes. Under the standard model, a black hole can only form when a massive star dies and collapses under its own weight. But primordial black hole theories suggest that immediately after the Big Bang, during the first chaotic microsecond of creation, The raw pressure of space was so intense and uneven that massive pockets of dark matter and energy were instantly crushed directly into black holes, skipping the star phase entirely. If the young universe was seeded with millions of these ready-made primordial black holes, they would have acted like massive gravitational vacuum cleaners scattered across the dark. They wouldn't have needed to wait for dark matter halos to slowly merge over hundreds of millions of years. They were already there on day one, heavy, hungry, and pulling massive clouds of gas into their centers at terrifying speeds. This could explain the impossible speed of galaxy building. These ancient black holes would have pulled gas inward so aggressively that they forced the creation of stars at a frantic, runaway pace, acting as the secret hyper-accelerators behind the skyscrapers Webb is finding in the dark. But even this theory feels like a desperate patch rather than a clean solution. If primordial black holes are real, we should see evidence of them closer to home. We should see them floating through our own neighborhood, warping the light of nearby stars, or disrupting the orbits of planets. So far, despite intense search efforts using every tool at our disposal, we haven't found a single definitive trace of them in the modern universe. They remain a ghost story, a convenient mathematical phantom conjured up to save a broken timeline. The deeper problem running through all of this is that the James Webb Space Telescope was not built to break physics. It was built to confirm it. For 30 years, the narrative surrounding the telescope was one of ultimate triumph. We were told that once Webb was operational, it would provide the final, missing pieces of a beautiful mosaic we had been painting since the days of Albert Einstein. We expected it to confirm that our supercomputer simulations were perfect, that our understanding of dark matter was flawless, and that the history of the cosmos was a smooth, predictable line of elegant evolution. Instead, Webb has acted like a giant golden wrecking ball, swinging directly into our complacency, and the public is catching on to the tension. For a long time, the wider world viewed space science as a settled, static subject. You open a textbook, you memorize the age of the universe, you look at a pretty picture of a nebula, and you move on. But right now we are witnessing something incredibly rare, a live, unedited, high-stakes crisis happening at the absolute frontier of human knowledge. It's a reminder of what science actually is. Science is not a sacred book of unchanging facts. It is an ongoing, messy, often uncomfortable argument with the dark. It is a process where you build the most advanced machine your species can conceive, launch it 1,000,000 miles into the void, look out into the unknown, and have the courage to admit that the data coming back makes absolutely no sense. The split in the scientific community is growing wider by the day. There is an almost generational divide happening in physics departments. Older, established cosmologists who spent their entire lives building, testing, and defending the standard model are working overtime to find subtle ways to fix the equations. They are tweaking variables, adjusting dust absorption coefficients, and looking for any possible way to make Webb's data fit into the traditional framework. They feel, understandably, that throwing out a model that has successfully explained 99% of our observations for 50 years because of a few early outliers is a form of scientific madness. But the younger generation of physicists is looking at those whiteboards with a completely different energy. They don't see Webb's discoveries as a problem to be solved. They see them as an invitation. They see an opportunity to be the ones who write the next chapter of physics. They are openly playing with radical ideas, that gravity changes its strength depending on the age of space, that dark energy is not a constant force but a living, changing field, and that our understanding of the Big Bang itself is just a crude approximation of a much larger, much weirder reality. And while the arguments rage on in the lecture halls and peer-reviewed journals, the telescope itself doesn't care about our existential panic. 1,000,000 miles away, out in the silent, freezing desert of the second Lagrange point, the James Webb Space Telescope continues its lonely vigil. Its sunshield, a giant 5-layer sheet of plastic the size of a tennis court, keeps the instrument cooled to a staggering -370 degrees Fahrenheit, ensuring that the faint heat from its own electronics doesn't blind its sensitive infrared eyes. It slowly turns its giant gold-plated honeycomb mirror, targets another random pitch-black square of empty sky, and holds its gaze for hours at a time. It collects the ancient, stretched-out photons that have spent 13 billion years racing across the expanding emptiness of space to find us. It registers each tiny drop of light, converts it into a digital signal, and beams it back across the void to Earth. Each new transmission is a fresh message from a universe that refuses to be simple. It is a universe that built its masterworks in the dark while it was still in the cradle. It is a universe filled with campfire smoke where there should be nothing but cold hydrogen, fueled by dark matter engines we can't see, and expanding at speeds that mock our finest mathematics. We wanted Webb to show us our origins, to give us a neat, clean story about where we came from and how we got here. Instead, it has given us something infinitely better, a universe that is still completely up for grabs. It has reminded us that we are still just children, sitting on the edge of a dark ocean, looking out at skyscrapers in the distance, realizing with an authentic, breathtaking humility that we don't know nearly as much as we thought we did. And as the data keeps streaming in, the only choice left is to keep looking, keep questioning, and prepare ourselves for whatever version of reality we have to build next. This breakdown of old frameworks has forced cosmologists into a territory that feels less like a structured science and more like a high-stakes detective story where every clue contradicts the last. If you look at the research papers coming out right now, the tone has shifted from cautious skepticism to a kind of breathless curiosity. We aren't just adjusting variables anymore. We are questioning the very nature of cosmic dawn, the moment the universe woke up. To truly understand how deep this mystery runs, we have to look closely at what happened right before these giant galaxies showed up. According to the Standard Model, the universe went through an era called the Cosmic Dark Ages. This was a period that lasted for a few 100 million years after the initial flash of the Big Bang cooled down. During this time, the universe was completely pitch black. There were no stars, no galaxies, no planets, and no light. There was only a cold, silent, uniform mist of hydrogen and helium gas drifting through an ever-expanding void. The standard story says that this mist was incredibly smooth. If you could have walked through it, one region of space would look exactly like any other region of space for millions of light years in every direction. It was a perfectly balanced, featureless soup. The only thing happening was that gravity, working at an agonizingly slow pace, was trying to find the tiniest microscopic ripples in this gas, places where the mist was just a fraction of a percent denser than the surroundings, and pull more gas into them. The transition from this perfectly smooth, dark fog to the first generation of stars is supposed to have been an incredibly delicate, drawn-out process. It's like trying to get a damp pile of leaves to catch fire. You need the gas to pack together tightly, but as it gets compressed, it heats up, and that heat creates pressure that pushes the gas back out. To make a star, the gas has to find a way to cool itself down so gravity can finish the job and crush it into a nuclear furnace. In a universe made of nothing but simple hydrogen and helium, cooling down is mathematically difficult and takes an enormous amount of time. But Webb's discoveries are showing us that this damp pile of leaves didn't just catch fire, it exploded into a raging forest fire almost instantly. The transition from a featureless fog to a universe crowded with massive, chemically complex, rotating skyscrapers of stars happened in what is, on a cosmic scale, a single weekend. This has led to an entirely new crisis involving something called supermassive black holes. Almost every large galaxy we see today, including our own Milky Way, has a monstrous black hole sitting directly in its center. These objects are millions or even billions of times more massive than our Sun. In the modern universe, we know exactly how they grow. They start out as normal-sized black holes when a giant star dies, and then over billions of years, they slowly eat surrounding gas and merge with other black holes, gradually growing into giants. It's a slow, steady diet. Yet when Webb looked back into the deep past, it didn't just find impossibly large galaxies. It found that these galaxies were already harboring fully grown, monstrous, supermassive black holes at their cores. One of these ancient black holes clocked in at a mass of over 1 billion suns, sitting in an era when the universe was barely a few 100 million years old. This completely shatters our understanding of how black holes grow. If you take a normal stellar mass black hole born from the death of the very first stars and feed it at the absolute maximum speed allowed by the laws of physics, ignoring the Eddington limit and letting it swallow matter as fast as humanly possible, it still couldn't reach 1 billion times the mass of the Sun in a few 100 million years. It's a mathematical impossibility. It would be like looking at a human baby that was born yesterday, but it already weighs 300 pounds. You would look at it and know, without a shadow of a doubt, that it didn't grow that big just by eating standard baby food for 24 hours. Something else had to have happened. This paradox has forced a radical new theory into the mainstream, the concept of direct collapse black holes. Instead of the traditional story, where gas forms a star, the star lives, the star dies, becomes a small black hole, and slowly grows. This theory suggests that the early universe skipped the middleman entirely. Under the unique, hyper-dense conditions of the early cosmos, massive clouds of gas containing the weight of hundreds of thousands of suns might have collapsed all at once, directly into a massive black hole in a single catastrophic gravitational event. If these giant seed black holes were created out of nothing during the dawn of time, they would provide an immediate heavy gravitational anchor for the first galaxies. They would act like giant whirlpools in the cosmic mist, dragging in millions of light-years of gas and forcing it to compress and ignite into stars at speeds we've never seen before. This would explain why Webb is seeing fully built, organized skyscrapers so early. The universe had giant gravitational magnets pulling the pieces together at hyperspeed. But as with every other escape route scientists have tried to take, this solution opens up a whole new can of worms. To make a cloud of gas collapse directly into a black hole without breaking apart into millions of smaller normal stars, the gas has to remain completely pristine. It cannot contain a single trace of heavy elements like carbon or oxygen, because even a tiny amount of those elements would cause the cloud to cool down too quickly, causing it to fragment into a normal cluster of stars instead of a single monster. And as we've already established, Webb is finding that the early universe was already heavily polluted with campfire dust and oxygen. The pristine, clean conditions required to make a direct collapse black hole simply don't seem to match the messy, chemically advanced reality Webb is revealing. Every time we invent a new piece of physics to save our timeline, the actual data from the telescope steps in and knocks it down. The tension has created an atmosphere in the scientific community that feels incredibly alive. This isn't a dry academic debate over decimal points. It is a fundamental struggle over our place in the cosmic story. For a long time, the Standard Model gave us a sense of comfort. It told us that we lived in a predictable, orderly universe that grew up in a way that our human minds could easily catalog, simulate, and understand. We felt like we had mastered the blueprint. Webb has thoroughly shattered that illusion. It has reminded us that the universe is under no obligation to fit inside our computer models or match the expectations of our peer-reviewed journals. We are looking at a reality that is far more dynamic, far more efficient, and far more mysterious than we ever gave it credit for. Some researchers are now suggesting that we might need to look at gravity itself through a completely different lens. For over a century, our understanding of the cosmos has been built on Albert Einstein's theory of general relativity. It is a masterpiece of physics that describes gravity not as a magnetic pull, but as the literal bending of the fabric of space and time by heavy objects. General relativity has passed every single test we've ever thrown at it within our solar system and our modern neighborhood. But a growing group of rebel physicists is starting to ask a dangerous question. What if gravity doesn't work the same way at cosmic scales as it does in our local neighborhood? What if across vast distances of billions of light years and during the extreme density of the early universe, the strength of gravity shifts? This idea is part of a framework called modified gravity. If gravity was subtly stronger or behaved differently during the first few 100 million years after the Big Bang, it would completely change the game. It would allow dark matter and gas to clump together at speeds that leave our current simulations in the dust. It would build foundations overnight, fuel star factories at impossible rates, and explain every single skyscraper Webb has found without needing to invent dark stars or primordial phantoms. But changing the rules of gravity is a terrifying prospect for most scientists. If you tweak Einstein's equations to fix the early universe, you risk breaking our understanding of the modern universe. If gravity was different back then, how did it transition into the gravity we experience today? Why does general relativity work so perfectly when we calculate the orbit of Mars or the path of a space probe if the underlying math is fundamentally unstable across time? It's a logical tightrope that no one has figured out how to walk without falling into absolute mathematical chaos. While the theorists continue to throw equations at their whiteboards, the engineers who manage Webb are focused on a much more practical reality. The telescope is working flawlessly, and its clock is ticking. Because Webb sits 1,000,000 miles away at the L2 point, it has to use its own onboard fuel to make tiny corrections to its orbit and keep its massive solar shield pointed perfectly at the sun. When it launched, engineers hoped the fuel would last for about 10 years. But thanks to an incredibly precise launch by the Ariane 5 rocket, Webb saved a massive amount of energy during its journey out into the void. Current estimates suggest the telescope has enough fuel to keep operating, turning, and looking into the dark for over 20 years. That means we are only at the very beginning of the rewrite. If Webb managed to cause a total crisis in the field of cosmology within its first few months of operation, imagine what it's going to turn up over the next 2 decades. We are going to get deeper images, sharper chemical barcodes, and larger samples of ancient space than anyone ever dreamed possible. The anomalies aren't going to go away. They are going to multiply. This is what makes this moment in human history so uniquely thrilling. We are living through a genuine scientific revolution in real time. It's easy to look back at history, at the moments when Galileo pointed his crude leather telescope at Jupiter and proved the Earth wasn't the center of everything, or when Edwin Hubble looked at distant nebulae and realized our galaxy was just one of billions, and feel like all the great overrides of human knowledge happened in the distant past. We think of those paradigm shifts as historical events that belong to black and white photos and old textbooks. But Webb is proving that we are right in the middle of one right now. The teenagers sitting in high school physics classes today are going to enter university departments where the textbooks are being actively rewritten on the fly. The old guard is defending a beautiful, century-old mosaic that is showing massive cracks, while a new generation is looking at those cracks and realizing that a much bigger, much stranger picture of reality is waiting to be painted. Every day, the radio dishes of NASA's Deep Space Network lock onto a faint, incredibly precise signal, coming from 1,000,000 miles away in the dark. It is a package of data traveling at the speed of light, carrying the digitized history of photons that left their homes 13 billion years ago. Those photons crossed an expanding void, passing by collapsing stars, drifting through clouds of campfire dust, and escaping the pull of ancient monstrous black holes, just to land on a series of golden mirrors suspended in the absolute quiet. And when we translate those signals into pictures and graphs, they tell us the same beautiful, humbling truth over and over again. The cosmos is not a solved puzzle. It is an infinite, wild, untamed frontier. It didn't wait for our formulas to be written before it started creating its most complex and structured masterpieces. We aren't masters of the universe's blueprint. We are still just beginners, standing on the shore of a vast ocean of time, realizing with a brilliant, authentic sense of wonder that the story of creation is far bigger, older, and more magnificent than we ever dared to imagine. The maps are burning, the models are cracking, and the true adventure of discovering where we come from has only just begun. This intellectual turbulence has forced cosmologists to reconsider not just the structures themselves, but the very nature of light and distance. When Webb records these impossible sights, it isn't just taking a picture, it is capturing a spectrum. By splitting the incoming infrared light into its component colors, scientists can read the specific chemical elements present in a galaxy, like a barcode. This brings us to a concept that underpins the entire crisis, the cosmic timeline itself. For a century, our calculations of how fast the universe grew depended on a neat, linear relationship between distance and redshift. But as Webb pushes further into the dark, that relationship is twisting into shapes that defy our existing software. We are finding that the deeper we look, the more the universe behaves like an engine running on a secret secondary fuel source that we haven't yet identified. To grasp the sheer scale of what is breaking down, we have to look at the sheer density of the early universe. In the Standard Model, the cosmos expanded rapidly after the Big Bang, diluting the hot, dense soup of particles into a vast cooling expanse. As the universe expanded, matter became less concentrated. It was supposed to take vast stretches of time for gravity to overcome this cosmic thinning and pull enough gas together to build something substantial. Yet, Webb is showing us that the early universe was a place of extreme, highly concentrated activity. It is as if the matter in the cosmos didn't expand uniformly, but instead condensed into hyper-dense pockets almost immediately. Think of it like a drop of ink falling into a glass of water. Instead of fading into a smooth, pale blue tint across the whole glass, the ink stays tightly packed, forming intricate dark ribbons and intense droplets that refuse to dissolve. These hyperdense ribbons of matter are where the impossible skyscrapers are standing. Because the gas was packed so tightly together, the physical distances between proto-galaxies were much shorter than they are today. Collisions, mergers, and gravitational interactions weren't rare events separated by hundreds of millions of years. They were happening constantly, a chaotic cosmic demolition derby occurring in a crowded room. This hyper-crowded environment created a phenomenon that is currently turning the study of star formation upside down: stellar cannibalism. In our modern, quiet neighborhood, stars live largely isolated lives. The distance between our sun and the next nearest star is so vast that they will never interact. But in the ultra-dense environments captured by Webb, stars were born so close together that their outer atmospheres were actively touching. Giant stars were feeding on smaller stars, merging together to create hypermassive stellar monsters that shouldn't exist under standard evolutionary rules. These cannibalistic stars burned with a fierce, blinding intensity, processing hydrogen into heavy elements at rates that completely throw off our chemical clocks. This could explain why Webb is finding heavy elements like oxygen and carbon so early. The star factories weren't running normal shifts. They were running hyper-accelerated, high-density operations where stars lived and died in a fraction of their normal lifespan. But even this high-density explanation runs into a major barrier: the laws of thermodynamics. When a massive cloud of gas collapses to form a galaxy or a star, it generates heat. That heat creates outward pressure, which fights against the collapse. To keep falling inward and building a massive structure, the cloud must get rid of that heat. It does this by radiating energy away into the surrounding space. In the modern universe, heavy elements like carbon, oxygen, and iron are fantastic at radiating heat. They act like a cosmic cooling system, allowing gas clouds to drop their temperatures rapidly, collapse efficiently, and build stars. But in the ultra-early universe, before those heavy elements were forged, the pure hydrogen and helium gas was an incredibly poor coolant. It held onto heat like a thick wool blanket. Mathematically, a pure hydrogen cloud should take a very long time to cool down enough to collapse. This leaves scientists trapped in a logical circle. To build massive, structured galaxies quickly, you need heavy elements to cool the gas down. But to get heavy elements, you need massive stars to live and die first. And to get those massive stars, you need the gas to collapse in the first place. Webb's data shows that the universe somehow bypassed this entire chicken and egg dilemma. It found a way to cool the gas and build the structures without waiting for the necessary chemical infrastructure to be installed. This mystery has brought a long-neglected concept back from the dead: tired light theory. First proposed in the late 1920s as an alternative to the expanding universe model, this idea suggested that the universe isn't actually expanding at all. Instead, it argued that light simply loses energy as it travels across vast distances of space, shifting toward the red end of the spectrum over time like a runner losing stamina during a marathon. For decades, the scientific community discarded tired light because it couldn't explain the smooth, uniform background heat left behind by the Big Bang. But a small number of physicists are revisiting a hybrid version of this idea to see if it can ease the tension Webb has created. They are exploring whether light might be interacting with an unknown field or particle in deep space, perhaps a component of dark matter or dark energy that causes its wavelengths to stretch faster than standard expansion would predict. If light stretches faster over long distances, it would mean that a galaxy with a high redshift isn't actually as close to the dawn of time as we think. A redshift of 14 might not mean we are looking at an object 290 million years after the Big Bang. It might mean the light has traveled through an energetic field that artificially aged it. If this hybrid model holds any truth, the impossible galaxies wouldn't be impossible anymore, because they would actually reside in a much older, more comfortable part of the cosmic timeline. However, proposing a change to how light travels through space is like pulling a thread on a sweater. The entire fabric of modern physics begins to unyielding collapse. If light loses energy or changes its behavior across space, then our measurements of the entire universe, our understanding of quantum mechanics, and the equations that govern nuclear reactions across the cosmos have to be called into question. It is a price most cosmologists are completely unwilling to pay. They would rather invent thousands of invisible primordial black holes or dark stars before they modify the fundamental behavior of a photon. While this theoretical warfare plays out in the journals, the sheer physical reality of Webb's observations continues to stagger the imagination. The telescope has begun targeting gravitational lenses, places where a massive cluster of closer galaxies acts like a giant, natural magnifying glass in space. The immense gravity of the cluster warps the very fabric of space-time around it, bending and amplifying the light from the truly ancient galaxies sitting directly behind it. By using these cosmic magnifying glasses, Webb can zoom in on the impossible early structures with unprecedented clarity. Scientists aren't just seeing the total light output of these systems anymore. They are starting to resolve individual star-forming regions within them. They are seeing the knots of gas where the first generations of stars were igniting. And what these magnified views are revealing is that these early galaxies are incredibly compact. They contain the same amount of mass as a modern sprawling galaxy, but it is crammed into a space that is 10 to 100 times smaller. Imagine taking the entire population, infrastructure, and mass of a city like New York and squeezing it into the physical footprint of a single neighborhood block. The gravitational forces inside these compact hypergalaxies would be absolutely terrifying. The stars would be packed so tightly together that the night sky from a planet inside that system would be a solid, blinding sheet of white light. The intense gravitational interactions would constantly fling stars out of their orbits, creating a volatile, high-energy environment unlike anything that exists in our modern, tranquil universe. This extreme compactness adds another layer to the dark matter puzzle. If these galaxies are that small and that heavy, the dark matter halos anchoring them must have been incredibly dense and sharp, acting like gravitational needles piercing the fabric of space, rather than the broad, shallow bowls we see today. This suggests that dark matter wasn't just clumping together faster in the early universe. It was clumping together in a fundamentally different shape. The psychological impact of these continuous anomalies on the scientific community cannot be overstated. For a generation, cosmology was a field of triumph. Scientists had mapped the leftover glow of the Big Bang to a fraction of a percent. They had built a beautiful, cohesive narrative called the Lambda CDM model, which used just a handful of numbers to explain the history, composition, and fate of everything in existence. It felt like the final victory lap for human curiosity. Now that confidence has turned into a radical, electric uncertainty. The most honest scientists in the field are openly admitting that we are back to square one on some of the most basic questions in astrophysics. We are realizing that our neat computer simulations, which we trusted to show us the history of space, were essentially just mirrors reflecting our own assumptions back at us. We programmed the computers to believe the universe grew slowly, so the computers built slow-growing universes. Webb went out into the real world and showed us that nature had a completely different plan. And yet, despite the chaos, there is no despair in the field. There is an unmistakable sense of joy. The breakdown of a model is the most exciting thing that can happen in science, because a model that works perfectly is a dead end. If your equations explain everything, there is nothing left to discover. It is precisely when the data punches a hole through your foundation that the actual work of genius begins. A million miles away, completely indifferent to our debates, our textbooks, and our fragile frameworks, the James Webb Space Telescope continues its silent dance in the absolute zero dark. It doesn't care that its data is causing arguments in London, Tokyo, and New York. It doesn't care that it has broken our understanding of time, dark matter, and stellar growth. It is simply a machine doing what we built it to do, catching the light that has been running through the dark since the beginning of everything. As its golden mirrors collect those ancient, stretched photons, it continues to paint a picture of a cosmos that is infinitely richer, faster, and more creative than we ever dreamed. It is a universe that didn't wait for our physics models to catch up before it started building its greatest masterpieces. We are privileged to be the generation that gets to watch the old maps burn, standing on the edge of a new frontier, realizing with a profound, beautiful humility that the story of our universe is still waiting to be written. The pressure cooker of modern cosmology isn't just leaking steam. The lid is about to blow off completely. When you examine the sheer volume of data the James Webb Space Telescope has beamed back, you realize we aren't dealing with a single, isolated anomaly that can be swept under the rug. We are dealing with a systemic structural failure across multiple independent lines of cosmic evidence. The skyscrapers standing in the dawn of time were just the opening salvo. Now, as teams around the world dig into the deeper, quieter channels of Webb's observations, they are finding that the very chemistry of pristine space, the behavior of cosmic magnetic fields, and the evolutionary tracks of the oldest stars are all singing the exact same rebellious song. To map out where the next fault line is cracking, we have to look at an elegant but deeply troubling phenomenon known as cosmic metallicity. In the language of astronomy, the word metal doesn't just mean iron, copper, or gold. To an astrophysicist, anything heavier than hydrogen and helium is classified as a metal. Oxygen, carbon, neon, nitrogen. All of them are metals in the eyes of a cosmologist. The Standard Model dictates that the early universe should have an incredibly low metallicity. It's a simple rule of compounding interest. If the Big Bang only provided hydrogen and helium, then the first stars had to start their engines with zero heavy elements. When those first monstrous stars died and exploded, they seeded the surrounding space with just a microscopic dusting of metals. The second generation of stars took that slightly dirty gas, compressed it, forged a bit more, and exploded again, adding another layer of pollution to the cosmos. This means that if you plot the chemistry of the universe over time, it should look like a smooth, upward ramp. The further back in time you look, the cleaner and more pristine the gas should be. But Webb didn't find a smooth ramp. It found a chemical cliff. When the telescope targeted a series of early galaxies sitting at a redshift of 10 and beyond, looking at an era when the universe was less than 500 million years old, it ran the incoming light through its spectrograph. This instrument acts like a chemical prism, splitting the infrared light into a hyper-detailed barcode where every single element leaves a distinct, unforgeable dark line. Scientists expected to see almost blank barcodes, showing nothing but the stark, clean lines of pure hydrogen and helium. Instead, the barcodes came back crowded with lines. Webb found staggering amounts of carbon, nitrogen, and oxygen floating in the interstellar mediums of these infant systems. In some of these early frames, the ratio of heavy elements to light elements is shockingly close to what we see in much younger, modern galaxies. This is a devastating blow to our timeline. To get that much carbon and nitrogen into the open void of space, you don't just need a few stars to explode. You need massive, sustained cycles of stellar life and death to have already run their course. Nitrogen is particularly problematic because it is primarily produced in intermediate mass stars during a specific, late stage of their evolution. These stars have to burn steadily for tens or even hundreds of millions of years before they can gently puff their outer layers of nitrogen into space. They aren't like the hypermassive monsters that live fast and die young in a spectacular explosion. They are patient, slow-burning engines. For Webb to find a universe already drowning in nitrogen at a redshift of 10 means the clock had to start ticking long before the Big Bang model easily allows. It implies that the cosmic dark ages, that silent, pitch-black era where the universe was supposed to be a cold, featureless fog of simple gas, must have been incredibly short, or perhaps didn't exist in the way we imagined at all. The moment the universe was born, it seems to have hit a cosmic fast-forward switch, bypassing the pristine stage entirely and rushing into a complex, dirty, chemically mature reality. This chemical maturity has forced a radical, almost heretical question back into the hallways of elite research institutions. What if the Big Bang itself wasn't the absolute beginning of our matter? A small but vocal group of theoretical physicists are dust-busting an old mathematical framework called the cyclic universe model. Instead of a universe that starts from an absolute point of nothingness 8 billion years ago and expands forever, this model suggests that the cosmos goes through an infinite loop of death and rebirth. It expands for trillions of years, slows down, contracts under its own gravity into a hyperdense crunch, and then bounces back outward in a new explosion. Historically, the biggest problem with the cyclic universe was that every time the universe crunches and bounces, it should carry over the entropy and heavy elements from the previous cycle. It would be like trying to build a new house out of the charred rubble of a burned-down mansion. The new house would look dirty and structurally cluttered from day one. But in light of Webb's discoveries, that historical flaw suddenly looks like a bizarrely perfect explanation. If the universe didn't start with a clean slate 8 billion years ago, but instead bounced out of a previous highly evolved cosmic era, it would explain why Webb is seeing fully built skyscrapers and heavy campfire dust right out of the gate. The universe didn't build those complex structures in 300 million years. It inherited the raw architectural blueprints and chemical remnants from the cycle that came before it. Of course, the math required to make a universe bounce without collapsing into an inescapable infinite black hole is incredibly fragile. It requires invoking exotic, undiscovered particles with negative energy states and breaking several fundamental rules of quantum mechanics. For most mainstream scientists, turning to a bouncing universe to explain a few oversized galaxies feels like burning down your house to get rid of a spider. It fixes the immediate problem, but it leaves you standing in the cold with nothing left. While the theoretical physics community fractures over whether to rewrite time itself, an equally bizarre mystery is unfolding in the study of cosmic magnetic fields. We don't often think about magnetic fields when we look up at the stars, but they are the silent directors of the cosmic orchestra. Magnetic fields wrap around galaxies, channeling the flow of gas, protecting forming star clusters from destructive cosmic rays, and determining how tightly material can compress to form new suns. Under standard physics, magnetic fields in space are created by a mechanism called the cosmic dynamo. It works just like the alternator in your car, or the spinning liquid iron core of the Earth. You start with a tiny, weak seed magnetic field, created by the random movement of charged electrons in hot plasma. Then, as a galaxy rotates, its giant spiral motion takes that weak seed field, wraps it around itself, stretches it, and amplifies it over billions of years into a massive, coherent magnetic shield. The rule was simple. Young galaxies should have weak, messy, unorganized magnetic fields. Mature galaxies should have strong, clean, structured ones. Yet when Webb combined its power with ground-based radio telescopes to analyze the polarization of light coming from the early universe, it found something impossible. It detected strong, highly organized, large-scale magnetic fields wrapping around galaxies that were less than 1 billion years old. These fields weren't weak or chaotic. They were fully developed, displaying the exact same strength and clean alignment that we see in the modern Milky Way today. This discovery has left dynamo theorists completely stranded. A galaxy has to rotate dozens or hundreds of times to stretch and amplify a magnetic field into a coherent structure. But a galaxy that is only a few 100 million years old hasn't had time to spin that many times. It's like looking at a beautifully spun, intricate spiderweb and being told the spider only started building it a fraction of a second ago. The physical mechanics of motion simply don't allow for that level of organization in that span of time. To fix this, scientists are being forced to suggest that these magnetic fields didn't grow inside the galaxies at all. Instead, they are arguing that the magnetic fields are primordial, meaning they were baked into the literal fabric of space during the Big Bang itself, before stars or galaxies even existed. If the universe was born already magnetized, it would mean that magnetism is not a byproduct of cosmic structure, but one of its primary causes. A pre-magnetized universe would change everything about how gas collapses and how the first stars formed, providing an invisible, high-speed track that could force matter to organize itself far faster than standard gravity ever could. But adding primordial magnetism to the Big Bang is another dangerous mathematical patch. If you make the initial magnetic fields too strong, you ruin the smooth distribution of matter that we see in the cosmic microwave background. If you make them too weak, they can't explain Webb's discoveries. The values have to be tuned to an absurdly precise degree, sitting on a razor's edge that feels deeply unnatural to scientists who prefer their laws of physics to emerge naturally rather than being manually adjusted to fit the latest observation. The deeper you go into these competing theories, the more you realize that cosmology is experiencing a profound psychological shift. For nearly half a century, the field was dominated by a sense of absolute certainty. We had built a model so precise that we could tell you exactly what percentage of the universe was made of normal matter, around 5%, what percentage was dark matter, around 27%, and what percentage was dark energy, around 68%. We felt like accountants who had successfully balanced the books of reality. Webb has shown us that our books are balanced only because we've been using creative accounting. We invented dark matter and dark energy to explain why our old equations didn't match the movements of modern galaxies, and now that we are looking at the early universe, even those invented placeholders aren't enough to make the math work. The anomalies are piling up faster than we can invent phantoms to explain them away. This tension has led to an incredible, high-velocity intellectual arms race between different research teams. Every week, a new paper lands on the preprint servers, offering a different, increasingly desperate fix for the standard model. One week, a team suggests that the early universe was packed with an exotic substance called early dark energy, a temporary burst of anti-gravitational force that accelerated the expansion of space right after creation, changing the way structure formed before vanishing into the background. The next week, another team counters with a model showing that dark matter particles are decaying into normal matter over time, meaning there was far more dark matter in the past to build giant halos quickly. It is a chaotic, beautiful explosion of human ingenuity, but it carries an underlying note of profound anxiety. Scientists are beginning to realize that the problem might not be with a single variable or a missing line of code. The problem might be with our core assumption about how we interpret the past. When we look through Webb's mirrors, we are translating infrared light into physical properties based on the physics we have learned inside our local solar system over the last few hundred years.